Okay, everybody, so please welcome Jules Damji. He's an Apache Spark community evangelist and a developer advocate at Databricks.
Can you guys hear me? Well, thanks a lot for coming to my session. I'm delighted to be here. Thanks a lot, Anaconda, and thanks a lot for Mike to inviting me. I'm going to talk about writing continuous application with structured streaming. Python, PySpark is the favorite word today. You probably heard it. The frequency count is very high, so I thought I would share the Spark love with you. I'm truly delighted to be here. You know, how can you not be in a city like Austin, which prides itself in being weird and staying weird? So I'm really, really happy to be here. So just a quick show of hands. How many of you are using Spark or you've used Spark in your production before? It's kind of hard to see. Okay, a few of you. You can actually, raise two hands. That make me feel a lot better. Well, thanks a lot. I know the answer to this question, but how many of you here are data scientists? None? Okay. How many of you are data engineers? And when I talk about data scientists, I'm talking about the data scientist definition that you actually heard today throughout the conference. It's one of those Venn diagrams that actually has all those three different things. Data engineers? Brilliant. So this talk is actually aimed towards both. So I just have an idea of what you are, and I'm just going to tell you a little bit of myself. I've had the great honor and privilege to really work with the original creators of Apache Spark from the early days at MPLAB, which then became the Apache Spark project. I was a developer advocate at Hortonworks. Before that, I worked as an engineer at one of the very early companies. And so I'm an old geezer, as you can tell. Lost all my hair and all that writing code. And now I'm out there pontificating. So I'm the guy on the left-hand side who wears the Obama father's baggy jeans and Converse and goes out and talks to people. That's my slides. So if you actually wish to follow me on SlideShare, you can actually take that and follow me if you actually want. So that's about who I am. The company I work for is the company that actually were the original creators of Databricks Spark, and is actually so today that big data is now in the forefront. We are actually at the zeitgeist of big data, and AI is really possible because of the fact that we can actually do that. And we actually provide you a unified analytics platform that allows you to do big data analytics, unified analytics at scale. And if you actually look at the core of the unified analytics platform, we have the Databricks runtime engine, which is really a collection of software artifacts that we have built on top of Apache Spark that actually gives you the performance and the reliability you actually need. And that sort of runs in. So if you're using even open source Apache Spark, which is that's what it is, when you run your Spark jobs on Databricks runtime engine, we infuse in it all the reliability and the performance you actually need. So that actually gives you the benefit. And we're available on Azure. As of about a month ago, we made a big announcement partnership with them, so you can actually use Databricks and the unified platform on Azure, as well as on AWS. And one of the other components that we actually have, what we call the Databricks serverless, and this is the ability for your administrator to actually create a large cluster to which you can submit jobs arbitrarily, and as a result of it being serverless, you can actually the serverless component part of it will actually shrink and expand. So that's actually available today, so you can actually do that. And for us to be actually bringing three sort of disparate people together, processes, platforms, and people, which is data scientists, data analysts, and data engineers, we provide a unified, what we call the Databricks worklist, which are really notebooks that allow you to sort of explore your data, allow you to train models in real time, deploy them, and then serve them in real time. So what are you here for today? Now, this is my agenda. If you go to any conference today, you're going to hear a lot about what big data has actually done to us. We heard about at the keynote what Peter talked about, how big data has actually changed and brought all these machine learning engineers and data science into the prominence because of the fact that data is available at massive scale. And it's not that AI is hyped today. AI algorithms and deep learning algorithms existed for a long time. If you go to the early academic papers, Geoffrey Hinton, who is really the father of deep learning, he actually created the prototype layer a long time ago. It's only now that because of the fact that we have big data and because of the fact that the hardware and the ability to actually create dedicated cluster to be able to do that in parallel processing is what data has actually done to us. And I'll just sort of very briefly give you an idea of what Spark is and why Spark actually has become, over a period of time, the de facto engine for you to do big data at scale. And then I'll sort of dive into why streaming applications is inherently difficult, and what structured streaming that we actually introduced in Apache Spark 2.0 has changed and addressed some of the challenges that we encountered in the early incarnations of streaming applications, and then give you an anatomy of what a continuous application actually looks like. And hopefully, if you have enough time, we'll give you a demo, and I'll try to answer the questions that you actually have if you have enough time. So just, this is today's madness per minute. This data is about 3 years old, but you can actually imagine the amount of data we're just creating online, right? Every 60 seconds. This is really madness. And you can imagine this is excluding, all the sensors that we have, all the gadgets that we actually have, all the trains and automobiles and planes, no pun intended, all this data that we've actually created. So if you actually include everything today that generates data, the projection by CDC in 3 years' time, which is down the road, just 2 years' time down the road, we will have dealing with 35 zettabytes of data. And 1 zettabyte is 10 to the power of 21. I mean, you can imagine, how do you actually deal with data at scale in real time? And how do you actually manage that? And you can't really do that in one machine. You can't do that in 2 machines. You need thousands of machines. And you have to have the plumbing and the ability and the infrastructure to actually deal with that. Which sort of brings us to this whole idea that because of this big data, machine learning applications have sort of pervasive, they permeated our lives, they predict our lives, they sort of dictate our lives for the good or the bad, depending on whether you actually believe in the whole notion of the tyranny of convenience, because this is actually giving us a lot of convenience, right? So if you go from left to right, if you look at, for example, AlphaGo, we didn't even think about AlphaGo as something that would be able to win against the champion of Go. And Go is deceptively a very simple game, but it's very complicated because it actually deals with a lot of intuition and deals with a lot of deep learning pattern recognition of how you're actually going to move that. We knew early on that we could actually train a machine to actually play games very effectively. The graphs was the first machine algorithm that was actually written that actually beat the graph champions around the US in the 1930s and 50s. And then came Deep Blue, which actually won against Garry Kasparov. And we started freaking out. He said, maybe the singularity is not very fair. And when this thing was actually released by Google that actually beat the world champion, there was a whole different era of our anxiety about how to actually deal with AI. Is AI going to take the world? Depending on what side of the world you are in. We are always confronted with recommendation engines that actually tell us what you should buy and what you shouldn't buy. Whether you go to Amazon, whether you go to Netflix. Today, Katrina talked about how they actually match suppliers and people who actually want to go home away. All these is actually propagated and done by a recommendation engine behind which you're actually doing data at scale. And all that's actually done in real time. You have continuous applications, which is really churning the data, scoring against the ALS algorithms that this recommendation engine use, and then gives you the recommendation in real time. The other thing, discovery, genomics. I mean, the amount of data that genomics actually generate that you can actually do drug discovery by analyzing the genomics, where you actually deal with, the deep forest that you have to deal with the curse of dimensionality. That's where it is. Character recognition. US Postal actually uses deep learning mechanism to recognize characters and zip codes. And then 2 Sigma is one of the very company that actually deploys all these machine learning algorithms to predict your stock predictions. And today, I think after this particular talk, if you have a chance, go and listen to Wes Kinnick, who is actually a contributor of Apache Arrow, that has significantly contributed to Apache Spark as well. And in Apache Spark 2.3, those of you who are actually writing UDFs in Python which was considered to be, a bad thing to do because of the fact that Python actually has to externally run on an interpreter and data comes back. But the Panda UDFs has done an incredible job, and it's all because of these guys at 2 Sigma who actually contributed that. And then you just go down the list. These are things now which are actually commonplace. Face recognition on Facebook, face recognition on Twitter. All these things you can actually tag because of the fact that we have data, because of the fact that we can actually deal with that. Now, the question you might ask, hang on, Jules. What has made that actually possible, right? Why is it, how you can actually deal with this particular data? And one of the reasons why you can actually deal with this data, that if you go to any one of the conferences, the term Apache Spark and big data, you will hear that in one sentence, right? Today, you actually heard a lot of people or across other tracks that you actually won. One of the items or one of the tools or one of the frameworks or one of the processing engines in the plethora of all the tools that actually are in the infrastructure, Apache Spark will always be there, right? Because of the fact that it has become a de facto engine. But I just want to spend about 5 minutes just to give you a historical context of why Spark came to be what it is today and where it is actually going in terms of its capacity and its capabilities. So what is Apache Spark, right? It started as a general-purpose computing engine based on the distributed paradigm that was actually introduced at Google a long time ago. And essentially, all it allows you to do is write functional programming that you can actually take your functions and then execute on the code, which is actually distributed across your particular file system. And there are two fundamental architectural principles that have sort of propelled Apache Spark in the forefront among developers like you. One is that it has a very rich set of APIs. APIs that allow you to do very declarative way to define what you actually want, not necessarily how you want something. So these unified APIs are across all the different workloads. And as a result of that, what we have done is, and when I talk about we here as a pronoun we, I'm talking about the Apache Spark community in general who have contributed quite a bit, and Databricks as well, because we are the largest contributors to the source code. And that has actually provided the unification engine. So what the engine has actually done is sort of decouple the workloads as a set of high-level APIs for streaming, if you're doing streaming. If you're doing ad hoc SQL queries, you'll get that. If you're using machine learning, right, you'll use those particular APIs. And as new workloads come in, for example, deep learning is a new workload that has actually come to the prominence because of the fact that we actually have all this data. And you don't have to have a separate engine to do that, right? You can actually run on top of Apache Spark that allows you to do the distribution at scale because of the underlying engine, which is actually built on MapReduce. And there's a large community of people who are actually contributing it, and you can deploy Apache Spark in all these different environments that it actually interacts with. But one of the unique things about Apache Spark is this concept of unification. And today you will hear a lot, any conferences you go to, unified analytics, big data analytics. And the unification engine is not something that the marketing term just came up. The unification was the underlying philosophy when Spark initially was conceived at AmpLab in Berkeley. And if you go back to the early paper that Jeff Dean, who is the father of deep learning and Google Brain, and Sanjay Gamwata, who produced this particular paper, they said, okay, now we want to index the entire world. How are we going to do that, right? We need 10,000 machines to distribute all the data, but we have to be able to actually not bring data to the machines, but we have to send code to the machine. So there was this MapReduce paradigm that was actually introduced, which is very fault tolerant, and all the necessity that you actually need was sort of introduced early on. And what they had actually initially an idea, they actually wanted to provide this as a general batch framework to do MapReduce at scale. And early in the paper, they actually made an observation that we were quite surprised that when we started writing this particular framework and providing that framework, we thought that we were just going to index only text documents. But people started using the MapReduce paradigm and APIs to do general batch processing. And unfortunately, what happened was because of that particular vision of them making that as a unified API, people both inside and outside Google started building these very separate systems, which were based on initially on MapReduce as the underlying engine to do general batch processing. And then start creating all these really silos, right? They created all these sort of specialized bespoke engines to do, for example, streaming, to do Impala for SQL, to do streaming for Storm, to do Mahout for machine learning. And underneath, if you actually look at that, they were all using MapReduce. Right? If you use, for example, Mahout to do your graph processing, you're not going to get the agency matrix right away to be able to show vertices and edge in your social graphs. You would have to grow through this large amount of log files to extract the pairs of agency matrix, and then you're going to give it to the graph to display that and to do some breadth traversal or create social graph. But underneath, they're all using MapReduce, right? And so the creators of Apache Spark, Matej Zaharie in particular, at Berkeley, sort of contemplated an idea, what is it about all these big data systems of yesterday that actually use the same thing? There's an underlying MapReduce paradigm that actually use. What is it actually that I can do that I can actually borrow from that? And what they did was sort of created an engine that sort of incorporated all the fault tolerances they actually need. They that all these engines actually use that. And then you did that all in memory. In other words, you actually provide all this MapReduce, we're creating the map, we're storing the data on the disk, they're reading the intermediate states, feeding into the next stage, and so on and so forth. So you sort of combine that in a very efficient manner. And the benefits were quite obvious. You as a developer just have to learn one language, because you can either do it in Python, you can do it in Scala, you can do it in Java, or you can do it in SQL, right? So it's easy to operate, it's easy to administer, because you only have one engine, you only have one set of configuration that you have to administer, and you don't have the complexity of Hadoop multiplied by n times for each and every that. So that sort of gave one of the benefits. The second benefit was code reuse, right? Because if you just have a simple engine that just is built on top of MapReduce, and you have all the fault tolerance built, you just have to write it once, you don't have to write it for each and every engine. Same thing with all the communication that actually happens between clusters and between workers and executors. All you just have to write it once, and if the monitoring that you have to do it once. So that code reuse was a huge benefit of the application. And the other thing was all these new apps were sort of built on top of that. So what really emerged was a very fast general purpose computing framework that gives you the ability to do functional programming in parallel in the language of your choice, Python being one of them, Scala being the reference implementation of the JVM, SQL, the ad hoc queries that you can actually do. You can use R, you can use Java, and you can deploy them in any of these environments that you can do it on cloud, you can do it on premise. And one of the analogies that I like to use is that some of us in this rooms are old enough. Well, I'm a geezer, so I know I used to carry all this like a geek. If you look at all these particular devices, they have three things in common. They have a video display on which you display the data. They have data in which they actually crunch. And they have a CPU inside, a memory chip or CPU on which you actually do the processing. And they use wireless to communicate. And all these were doing the same thing, but they had different APIs. So if you wanted to write an application with Palm Pilot, you got to learn Palm Pilot API to actually do that. If you want to write something for GPS, you would actually use that. All these video graphs. And what came was this, Apple iPhone actually changed the whole notion of unification. They provided one particular platform, iOS in this case, and then Google came up with Android. So all they actually had were you had one platform. You either write it on Java SDK or you write it on iOS, and you build application on top of that, right? So you got the idea of unification. If you look at Unix, how it actually emerged, you had one platform, you had one C++ or C APIs, and you had all these different applications that actually could run on the platform. If you can do this for mobile computing, why can't you do that for distributed computing? So that was the whole philosophy earlier. It's a very prescient idea by Matej Zaharie, who said, this unification was something that I had to think about very early on. And today, that's what Apache Spark is. It's a unified analytics platform that allows you to do big data processing at enormous scale. Now you might say, hang on, Jules, what has that got to do with streaming? You're here to talk about writing streaming applications. But I just wanted to set the context that Apache Spark gives you the merits and the benefit to actually do that. Now, streaming applications are inherently difficult because if you actually want to build robust streaming applications, those are actually really hard. Because if you think about streaming applications that actually run in real time in production, they don't exist in isolation. You're not going to write a stream that comes in, you're going to do something, you're going to send it back to the stream. They work in conjunction and in comport with all these other different components. You might have a stream come in, you might do some ETL, you might want to interact with the machine learning to do the scoring, you might want to write something on the disk, you might want to generate a particular report, or you might want to do ad hoc queries, right? All these are parts of the data pipeline that exist as a continuous application. And in order to do that, it's not very easy, right? Because there are three challenges that you have to deal with, right? When you're writing continuous application, because there are too many moving parts, and you have to address those. And what are those? And they actually come in sort of the three challenges. One is data is complex, right? You know it already. You've been here. You heard about it. You deal with it. Data is complex because it's diverse. They come in different format. They come in binary, they come in text, they come in Avro, they come in JSON, they come in CSV. They come in all different kinds of format. And you have to account for that. You have to have the ability to handle that. You have to have the ability to give the developers the right APIs to be able to deal with that. And then second, data can be dirty. Right? If you ask any data scientist today, what is the maximum amount of time you actually spend your day-to-day activities? You're going to do two things. I clean the data a lot. It's like janitor. I have to clean the data because it comes dirty. It might be out of order, right? Because you might have data coming in out of order because of latency or network failures. So you have to account for that. You have to account for the fact that it's complex. You have to account for the fact that it's late. And you have to account for the fact that it is out of order. The second thing that you have to deal with, the second challenges they have to deal with in writing application is the fact that streaming applications don't exist in isolation. And I made that assertion earlier. They exist in conjunction and in collaboration with other components. So you have to have the ability to actually provide a streaming application that can interact flawlessly in a fault-tolerant way with other combining applications that constitutes an entire continuous application. And then finally, systems are complex, right? When you're dealing with pipelines, when you're dealing with infrastructure, you know, your pages duty are going up. Systems fail. How do you account for that, right? You have diverse sort of storage system you deal with. You're reading from Kafka, you're reading from Kinesis, you're writing to RDMS, you're reading from RDMS, you're reading from S3 buckets, you're reading from HDFS. All these can actually fail. And you have to account that. How do you actually handle that? The engine has to be able to say, where I failed, I know where I failed. If I start my job again, I'll pick up from where I left off. And so I think that's very important. And these three challenges were something that we actually had to deal with. And so the Spark community and Databricks sort of in Apache Spark 2.0 said we have to change the underlying architecture of streaming and Spark SQL so we come up with a very fast, very tolerant engine that can provide the bedrock of all the structured APIs that actually sit on top of that. And so in 2.0, we actually went through this massive architectural change to be able to provide two components as part of the Spark SQL engine. One was the Catalyst analyzer, which takes your query and creates logical plans and physical plans, and then executes on using the Tungsten engine to generate the most efficient bytecode. So that sort of provided as one of the ways you can actually provide the fault tolerance, because that you write the query, whatever language you use the query, the SQL engine will be able to generate the code for you. And because of the SQL engine, which was the bedrock, we created high-level unified declarative APIs on top of that would allow you to address workloads. So you can do machine learning, for example, using the high-level API. You can do streaming using a high-level API. You can do SQL 2013 compliant SQL commands using the high-level APIs. They all undergo the same journey. They all generate exactly the same code. So that was the beauty. That's how we actually handled the ability to actually do complex work. So you can actually use machine learning. You can use other workloads at the same time. And the third challenge was we provide a data source API so you can actually read and write to all this complex system with the transaction built in. So if you're writing the RDMS, we actually make sure that when you wrote something, we honored the transaction so that you either write something or you don't, right? So that sort of gives you the fault tolerance. And you, as a developer, need not worry about reasoning to write structured streaming. And the model is very simple. If you look at it conceptually, What we did with structured streaming is that think about your stream as nothing but an unbounded table of data frames. If you think your stream as an unbounded table within the physical limit of the universe and your machine, you can make queries as if you were querying a static table or whether you're doing a streaming. So that sort of simple notion of saying, I can just make my queries as if I'm talking to a static table that's in memory, and I'm going to make my transformation. And we sort of append new queries, they actually come in. And you as a developer need not worry about the underlying infrastructure. That actually is taken care of. Spark will do that for you. The SQL engine will do that. The structured streaming engine will actually do that for you. You just write your transformations at a high-level API queries that we actually give you, and you tell Spark what to do and not how to do it, and it'll do it for you. Right? It acts as a compiler. So how is it actually done underneath? Here's a very simple Python code. All I'm doing is I'm reading from Kafka. Right? That's my first. I'm going to read from Kafka. I'm going to do some sort of a transformation. I'm going to read my devices, which are part of a JSON file. I'm going to signal out, or I'm going to filter out a particular device, and the signal is greater than 15. And once I'm done that, I'm going to write it back to Kafka, a very simple transformation. Underneath, what happens is that the Spark SQL engine is going to create a logical plan. This is no different than if you were using, say, SQL and Oracle or a huge RDMS database on a massive parallel processing. The SQL engine will actually parse your queries and create an operator tree, and it will rearrange the code when it actually goes to the optimization. The same thing, that's what Spark does. It acts as a compiler. It will parse your query. It will create a logical plan. And then what it will do with the logical plan, it will go through the cost-based optimizer to create the most physical optimal plan by attaching weights to it. That if I arrange my operator in some way, what is the best optimal solution that I can actually use to execute that? I could reorder that. I could rearrange the code. If this is talking to a database, I can push down predicates to the database to do filter or to do join, because the database is far more efficient to do join than your Spark will be able to do that. So pushing down to the place where it actually does that gives you the benefit of taking advantage of your data source. So that's the physical plan that actually creates. And then finally, what it does is that as the batches get accumulated, as the time frame goes out, you're reading from Kafka, you're creating your Kafka mode, you're executing it incrementally, and as time goes by, every batch is actually executed depending on how often you actually provide the trigger. So that's sort of what we call Apache Spark streamifies your queries if you're dealing with structured streaming and if you're writing a continuous application that has to run forever and dealing with other things. And that's sort of the very simple mode, but all the complexity is actually underneath, hidden from you. Now, in 2.0, we introduced this notion of in 2.3, we introduced this notion called continuous processing. What does continuous processing mean? If you have high latencies, or if you have latencies which are tolerable from 100 to 200 milliseconds, the default mode is structured streaming, which is already GA. People actually use it in production. We have customers use it at millions of records. They do that in production in what we call the structured streaming mode, which is the micro batching. So you get batches. You don't worry about the batches. It just automatically does that for you. The new mode is called continuous processing. And this is an experimental mode. Normally, the way we actually release things in the communities, we actually have experimental APIs so people can actually give us feedback. So this continuous mode is the ability for you to actually try that in continuous mode, which means that it's going to continuously run as data comes in. And if you look at it architecturally, the default mode is that you got a driver that actually reads at each epoch when the trigger goes off, and it will take those particular batches and give it to the executor to read that and do your computation. And at each epoch mode, it will actually do a checkpoint so that the driver knows that, okay, I've finished reading certain offsets, and I'm going to checkpoint that. The continuous mode is slightly different, except that it's going to have a long-running process that's continuously running on all the executors, and the driver says, oh, here's the data arrived, go and read it. Here's the data that's arrived, go and read it. It's going to continuously read that. Think of it as if you're writing network programming, and if you actually a select call, you normally in your typical network application, you select on a particular file descriptor, and an interrupt happens, the kernel will send that application to you, and you're going to write that. So it's like, continuously running that, and it will just block when there's no data on it. So how does it actually translate to doing streaming ETL in production at scale? So I'm just going to give you a very short example because there's no example devoid about word count. Here's an anatomy of a typical application that you're actually going to use in continuous mode. The first thing you're going to provide is you're going to provide the sink. You're going to provide where you want to read the data from. In this particular instance, I'm actually reading it from Kafka. So I'm saying, here's my source. Here is my topic that I'm going to read from, and go and load that particular into a data frame. So I'm going to read it from Kafka. The second step is you're going to make a transformation, right? You got your data frame, and now you want to do some sort of transformation. Whether you are doing filtering, whether you're actually doing some computation, whether you're doing some aggregation. In this case, we are doing aggregating. We're taking the value, which is the workload in our Kafka, we're converting into some column called key, and then we're doing aggregation count. Very simple API. If you actually had to write this in RDD, you probably have a cured insomnia. It'll just put you to sleep. But this is your transformation actually happening. The third thing you're going to do, once you're done with that, is you're going to provide some sort of an output mode where you want to write the data to be written. You want to write to the RDMS, where you want to write and store in a Parquet file, or whether you actually want to just put it down the stream to another topic in order for it to, another application down the stream can actually do that. And this will actually happen in a continuous mode. And there are some other administrative things that you can actually provide. You can say, for example, I want different kinds of output mode, right? So if you're doing a lot of debugging, you probably want to use what we call complete mode, where everything it has seen so far, it will do the aggregation, and it will just dump it out for you. But most people actually use update mode, which meant just change the rows that have changed, change the rows that have come in the stream that I've already seen it, but just aggregate that. And the ones that are new rows that come, just do an append at the end of the stream. So those are the different output modes that they actually provide. And the next thing you're actually going to do is you're going to provide some sort of a trigger. How often do you want your batches to be executed? Remember, I gave you the little epoch. Those are the batches in every 1 minute, every 5 seconds, every 1 second, every 3 seconds. Depending on what your latency is, you can actually define that. And it will create micro batches. And every 1 minute, it will execute your query in the incremental manner that we actually showed. But if you wanted to do that in continuous mode, all you have to do is just change this particular line, right? Instead of saying trigger 1 minute, say run it in continuous mode. And it will just use a continuous mode. And the 1 second is not that it's going to read every 1 second. 1 second is how often do you want to checkpoint that? So we can actually maintain some sort of a sanity and fault tolerance. So we can say, okay, you've seen this data before. It's exactly one semantics. So that's what continuous mode for 1 second is. It is not that it's going to create a batch for 1 second. It is how often it's going to checkpoint that thing for fault tolerance. And the whole idea behind checkpointing is really the ability for us to give you end-to-end exactly one semantics, because we keep track of what you have read and what you have not read. So when it actually fails, the driver knows, okay, this particular executor has already read these kind of offsets of a log file or of a Kafka stream or of an Oracle database. I'm not going to read that because you already read that and you already written that. And I've checkpointed that. So I'm going to give you where you actually failed. So that's one way of actually, or the way of maintaining checkpoint, which is maintaining the write-ahead log. So that was sort of a simple example of giving you the ability to write a very simple continuous application. But life is not easy, right? Life is complex. What do you do when you actually have lots of streaming data coming in? Now, traditionally, I mean, if you're a data engineer over here, the common platform or the common way to architecture the thing was using what we call lambda architecture, where you have sort of two paths of your processes. One is handling the streaming data that's coming in and is dumping out to a temporary file. And then you have other jobs which actually run in the background that take that particular streaming data and then write it either to some storage or some table so that your data scientists can then actually take that particular data and deal with it, because now you have sort of cleaned up certain aspects of data. This is not to say that they won't be dealing with that, but this is something that you actually do the ETL and then give them the pristine data so they can do feature engineering and feature extraction and all that. So data comes in raw. There is unstructured data and structured data, you put it, dump it into files. You have this periodic jobs that actually run. And then sometimes there is, unfortunately, hours of delay because that's a very brittle way of doing things. Things actually break. And if you have latency requirements, this becomes probable because if you're dealing with intrusion detection, if you're dealing with anomaly detection where you actually require latencies which matter to you, then this particular traditional way of doing ETL won't work, right, if you're a data engineer. But if you do it through streaming, you have the ability to actually text structure streaming, write your ETL right away, and then update the data right away that's available for you to do anything down the stream. And that's the whole idea behind using structured streaming, so you can actually do this in a very continuous manner. And we've got time. So this is a very typical canonical example of, import the stuff from PySpark, go ahead and read the stream, parse the data from Kafka. You're going to take that particular, the workload that you actually have, which is always the value. You're going to cast it to a string, and then you have all this high-level Python API from JSON to JSON, explode your particular schema. Do your ETL over here. Once you actually explode that into a data column, and I'll show you what it looks like, then you can actually select, and you can do project, and you can do filter, and you can do aggregation, and whatever you actually want in this continuum manner. Or you can actually have windowing functions that say, give me all the data on this particular devices that exist between certain time frames. All this can actually be done in real time, right? And then once you have done with the parse data, once you've cleaned the data, you might want to sort of, write it down, say, partition by date, and in this continuous mode, and then write to the particular Parquet file and then start your particular job. So what happens is, as you saw in that particular parsing mode, this is the data frame that you actually get when you read from Kafka, right? All the other columns are sort of, Kafka keeps track of it internally as because it's like a big queue. It always writes different partitions. And this is for Kafka, but you're interested in that value column. Right, so value is your binary encoded thing. It's normally in JSON. People normally send nested JSON or structured data. And what you do over here, you just read that particular data. And when you do the from string, selection, when you do from string JSON and use the particular schema to read that and expand it as a data, what you actually get is one column called JSON. But then when you do a from screen, it's going to expand that into individual columns that your JSON has. And if it has structured data, it will have multiple columns within that. And you can use all these little APIs that we actually provide in PySpark, in Scala, in Java, that you can actually select individual items that you actually need one. So if you have a very complicated nested structured JSON that you actually provide as part of IoT devices, this is how you actually parse that. And it's really powerful. I have some set of APIs. I have some blogs. I have some tutorials that actually show you, how you read something from Kafka that has very nested infrastructure. I use nested I/O devices that I read from Kafka, and I try to aggregate and find out, what my temperature is going to be. And you can use these APIs, which are part of PySpark, which are part of Scala, which are part of Java, that you can actually use that. Now, the links are in the PDF. You should be able to actually get that if you want to try that. But that's the whole idea behind the ability to actually write continuous streaming. And then you can actually write it to Kafka. You might want to write it to Kafka. You might want to write somewhere else. But that's the whole point. Now, I'm going to show you a quick demo. And those of you want to get this particular notebook, that's the particular URL. It's called databricks.co. ss_mllib_py, right? I had to actually do that because of the URL, so you won't be able to see it. So let me just give you a quick demo, because we got 12 minutes. All right, so this is, can you guys see it? All right, this is our Databricks notebook. When you log into the Databricks, this is the front page you actually get. We are a managed host service. We provide unified analytics at a platform. This is our interface to the cluster. You don't have to worry about it. You as a developer just deal with that, right? So on this particular side, you got all these different panels that you can actually use to create clusters. But I already have a cluster created, so I'm just going to go to my recent notebook and we can get started, right? So I'm going to give you an example of what this particular notebook looks like, right? This is a very short example. And this is what we talked about continuous earlier, right? I have the ability to read from Kafka or the files. Since I don't have a Kafka cluster running, I'm going to simulate that particular stream by reading it continuously from a directory atomically as files come in and simulate the stream. I'm going to do some ETL. I'm going to create a model, and I'm going to do scoring in real time. And then at the same time, do some ad hoc queries all within the context of running continuously, right? So the data I'm going to use is I borrowed it from the University of Brussels, the Uni de Brugge, where they actually have a machine learning group that was doing data mining, and they wanted to find out how to detect